Welcome to this explainer. You know, the device you're using to watch this right now, whether it's a smartphone, a laptop, or a smart TV, is powered by microchips that are practically invisible to the human eye. It's incredibly easy to take these everyday devices for granted, just tapping away without a second thought. But have you ever stopped to wonder why front-end semiconductor manufacturing is universally considered the most critical, most complex, and undeniably the most expensive industry on the planet? Today, we're going to uncover the staggering complexity and the mind-boggling economics behind how these tiny marvels are actually made.
Okay, let's just dive right into it. To truly understand the sheer stakes of this industry, consider this astronomical figure, $16 billion. That is the conservatively estimated capital required just to build one single modern 12-inch 5-nanometer semiconductor fab. And we aren't even talking about the research and development of the chips themselves. We are talking about just constructing the physical factory, pouring the specialized concrete, and installing the hyper-advanced machinery. It is a massive, almost incomprehensible amount of money concentrated into one highly specialized facility. And because of that immense upfront hardware cost, the ongoing financial pressure inside those walls is absolutely relentless. If we amortize that $16 billion over a typical 5-year equipment lifespan, a factory loses roughly $110 in depreciation every single second of unplanned downtime. Just pause and think about that for a moment. 1 second of a system glitch, $110 gone. An hour? That's hundreds of thousands of dollars just evaporating. And unplanned downtime isn't just a catastrophic machine failure. It could be a microsecond power blip, a slight mechanical alignment error, or even a minor software hiccup. This relentless financial math is what keeps the tension so incredibly high. It demands absolute, unwavering perfection day in and day out.
So today we're going to use a simple, data-driven approach to completely demystify this front-end process. We'll walk through 5 parts: the tech relay race, the $16 billion fab, extreme material science, measuring the invisible, and finally, the final test and beyond.
Let's kick things off with Section 1, the tech relay race, mapping the electronics value chain. Think of the birth of any electronic product as a massive, highly coordinated relay race. It starts at the very beginning with IC design companies. These are the architects creating the complex blueprints. Once those digital designs are finalized, the baton gets passed to the front-end fab, which really acts as the beating heart of this entire ecosystem. This is the crucial stage where blueprints for billions of tiny transistors are physically carved onto raw, circular silicon wafers. After surviving that grueling process, those fragile wafers are passed to back-end packaging to be precisely sliced apart and encased in protective shells. Next, they move to PCB assembly to be soldered onto circuit boards, and ultimately they're integrated right into the final product you hold in your hand. The front-end fab is the undeniable core of this race. It's the crucible where pure imagination actually becomes physical reality. Moving on to Section 2, the $16 billion fab, and why automation is everything. Remember that $110 a second loss we talked about a moment ago? Because the cost of failure is so astronomically high, a fab relies on a computer-integrated manufacturing system, or SIM. This is the fully automated digital nervous system of the factory, dictating every single movement and process. To avoid hemorrhaging money, fabs require this overarching software to maintain a staggering uptime of 99.99999%. To put that into perspective, that equates to less than 32 seconds of allowable downtime per year for an entire, sprawling mega factory. Stability isn't just a goal here, it is literally their highest guiding principle. So why exactly is this environment so exceptionally complex to manage? Well, unlike traditional factories where engineers can just jump in and manually fix an assembly line, the front-end fab is a fully automated, completely sealed environment. Wafers move entirely automatically in closed, ultra-clean boxes called FOUPs, zipping along overhead tracks. There is virtually zero human intervention allowed on the line because we humans introduce unpredictable variables, like microscopic dust, which are absolutely lethal to the chips. Furthermore, manufacturing modern advanced chips requires anywhere from 1,000 to over 1,200 completely separate process steps. Add in the fact that the system must intelligently juggle multiple different product types running simultaneously to maximize those expensive machines, and trace exactly which specific machine chamber a wafer passed through weeks ago for quality control. The logistical complexity is just staggering. Let's move to Section 3, Extreme Materials Science, Building Nanostructures. To truly understand what's happening inside those specialized machine chambers across all those steps, we need a fundamental mindset shift about what the word manufacturing actually means here. Traditional back-end assembly is what we typically picture, right?
It involves managing a complex bill of materials, taking pre-made physical puzzle pieces and soldering them together. But the front-end fab operates in a completely different paradigm. It's an exercise in extreme materials science. Instead of putting physical pieces together, it relies on the chemical deposition of ultra-thin films, the optical lithography of printing unimaginably tiny patterns with light, and the physical etching away of materials with plasma. It is literally carving and stacking nanoscale, three-dimensional structures layer by layer using aggressive chemical and physical reactions. Think of it kind of like building a microscopic 100-story skyscraper on a foundation the size of a pinpoint, where every single floor has to be structurally flawless.
Which brings us to Section 4, measuring the invisible.
Since this entire process relies so heavily on invisible chemistry and physics to build these structures, how do engineers actually measure their success before the chip is fully finished? Well, for the vast majority of those thousands of steps, the wafer doesn't actually have measurable electrical properties yet. It's just a chemical and structural work in progress. So engineers have to rely on a mountain of non-electrical, physical data to ensure things are on track. They constantly measure film thickness to guarantee that the materials deposited are perfectly even across the entire 12-inch disc. They meticulously measure the critical dimension, checking the incredibly tiny line widths and trench diameters right after etching. And they obsessively monitor the defect or particle count. At this minuscule scale, a single speck of dust dropping onto a nanometer scale circuit is like a massive boulder crushing a multi-lane highway. It destroys everything it touches.
But perhaps the most critical physical metric of all is called overlay. Think back to that 100-story building analogy we just discussed. Overlay refers to the extreme precision required to perfectly align a newly printed layer with the microscopic pattern on the layer directly beneath it. If the support pillars on the 50th floor of our nano skyscraper don't perfectly align with the foundation on the 49th floor by even a single nanometer, the entire circuit is compromised, potentially shorting out and ruining the final product. Now, this brings up a truly fascinating problem. Probing and measuring these extraordinarily delicate nanostructures with high-powered lasers or electron beams could actually destroy the customer's proprietary intellectual property or physically damage the very product they're trying to protect. So, how do they measure it safely?
The answer lies in some seriously ingenious workarounds. Rather than risk the actual product, fabs cleverly use proxy targets called test keys. These are specialized test patterns printed in the tiny, empty grid spaces between the actual chips, areas known as scribe lines, which are destined to get cut away by diamond saws and thrown out later anyway. Engineers scan and measure these test keys instead of the real chips. Additionally, they use sacrificial monitor wafers, which are just blank pieces of silicon run through a machine to strictly verify if things like temperature, gas flow, or etching rates are drifting out of spec. They also employ dummy wafers simply to fill empty slots in a batch carrier, ensuring that airflow and thermal dynamics remain perfectly stabilized during processing. It's an incredible, highly orchestrated web of indirect monitoring.
Finally, Section 5, the final test and beyond. After surviving over 1,000 physical, chemical, and optical hurdles, the resilient silicon wafer reaches the absolute end of the front-end process. Before leaving the fab, it undergoes a wafer acceptance test, or WAT. This is a monumental moment because it's the very first time real electrical currents are applied to check basic voltages and resistance. But the target is key here. It only tests those throwaway test keys on the scribe lines we just talked about. And it uses a strategic sampling method, just checking a few spots across the wafer to ensure the overall manufacturing process remains structurally and electrically healthy. This is completely different from the wafer sort and final test happening later at the back-end facility, which meticulously tests 100% of the actual, real product dies to rigorously screen out any bad chips before they ever reach the end consumer. All of this extreme material science, unbelievable automation, and precise measurement leaves us with a really provocative thought as we wrap up. As our microchips continue to shrink past 2 nanometers, pushing down toward the scale of individual atoms, what we call the 0.1 nanometer or Angstrom era, we are slamming right into the absolute limits of quantum physics. Will our current optical and electron beam measurements even be enough, or are we on the precipice of needing entirely new, perhaps quantum sensing models to measure the invisible future of technology? It's a massive, incredibly expensive challenge that will undoubtedly determine the next era of semiconductor dominance. Thank you so much for joining me on this explainer. I hope it gave you a powerful look into the $16 billion heart of your everyday electronics.